lift the pen somewhere to complete the graph. See, this is the graph of a continuous function. Here, one can complete the graph in a single stroke. That is, without lifting the pen from the paper, one can complete the graph of a continuous function. Now let us consider the graph of a discontinuous function. Here we cannot draw the graph in a single stroke. We have to lift the pen from the paper to complete the graph like this. This is the property according to geometry for a discontinuous function.
Let us consider the function f, which is defined by f of x is equal to x for all x element of the set of real numbers. We know that this function is the identity function. We shall show that identity function f is continuous. So, let C be any real number. Let C be any real number. Any real number. Then clearly function f is defined at C, and f of c. What is f of c? We know what is f of x. F of x is x, so f of c is a c only. Also, let us consider limit f of x as x tends to c. Then what is it? That is equal to limit of x. Why it is? Because fx is x only. Therefore, limit of x as x tends to c, that is equal to, we know this limit is c only. So what we can conclude here is limit of fx as x tends to c is equal to c, but c is nothing but f of c. So we can write like this. So what happened? That is limit of the function as x tends to c equals value of the function at c. Therefore, we can conclude that f is continuous at c. But what is c? C is any real number. So that is function f is continuous at every real number. That is function is continuous at every point in the domain. So simply we can say the identity function is continuous. Now let us consider the function f defined by f of x is equal to modulus x. Here again x belongs to the set of real numbers. That is the domain of the absolute value function, or modulus function is the set of all real numbers. And we are going to show that function f, that is modulus function here, is continuous. So here you know the total domain, we can divide it into three parts, that is 0 as a special case, negative real numbers and positive real numbers. First of all, we shall consider the 0, that is case 1, x equals 0. So clearly, what is the value of the function at x equal to 0? That is f of 0 is equal to modulus 0, that is equal to 0. So we got the value of the function at x equal to 0. And we know that the definition of the modulus function is that f of x is equal to negative x if x less than 0 and positive x if x greater than or is equal to 0. That is very simple. If x is negative, for example, x is equal to say negative 5, then what is the value? Function says that is negative x. X here is negative 5, so that is negative, and x is negative 5, so it becomes 5. And similarly, we can find the modulus values of the other numbers like this. And now we are going to find the left hand limit, that is LHL is equal to limit of fx as x tends to 0 minus. And you know, when x is tending to 0, taking values less than 0 means x is nothing but a negative number, x less than 0. So what will happen to fx then? Then fx is a negative x. So limit of negative x as x tends to 0 minus, that is equal to 0. So left hand limit is 0. Then we can find the right hand limit. So what about the right hand limit here? Right hand limit is equal to limit of f of x as x tends to 0 plus. So that is equal to limit x tends to 0 plus means x is slightly greater than 0. That is, x is positive. So what is the value of fx here? So fx here will be x only. So that is limit of x as x tends to 0 plus, that is 0. So we see that the left hand limit and the right hand limit are having a common value. Therefore we can speak of limit of fx as x tends to 0 is equal to 0, and it is nothing but a f of 0. So we could prove that value of the function at x equal to 0 equals the limit of the function as x tends to 0. Therefore function f given by a modulus function, that is mod x, is continuous at x equal to 0. Now case second. Let C be any negative real number. Let C be any negative real number. Negative real number. That is C less than 0. Then what about the f of C? F of C is equal to mod C. But C is negative here. Therefore that is equal to negative C. I told you modulus x is equal to negative x if x is negative. So here C is negative. So modulus C is equal to negative C. Now what is the limit of the function f of x as x tends to C? So that is equal to limit of x tends to C. And you know here fx is a negative x, because x is becoming C and C is negative. So fx is negative x. So that is equal to limit of negative x as x tends to C, that is negative C. Then what we see is that limit of fx as x tends to C is equal to negative C, that is equal to value of the function at C. Thus function is continuous for all C here, that is function is continuous here for all negative real numbers. Thus f is continuous for all negative real numbers, for all negative reals. Then we shall consider C be a positive real number. So consider as the case 3. Let C be a positive real number. C be a positive real number. Then what about the value of the function at C? That is modulus C is equal to C only, because C is positive. Then what about the limit of fx as x tends to C? That is equal to limit of. Here fx will be x only, because C is positive. So as x tends to C, that is equal to C. Again we could prove that limit of fx as x tends to C is equal to C is equal to, you know, that is nothing but value of the function at C. So we could prove that value of the function at C equals the limit value. Therefore function f is continuous here. F is continuous at all C that is positive here, at any positive real number. Any positive real number. Thus, we could prove that the function is continuous at every real number. First of all, we could prove it is continuous at 0, and then we could prove that the function is continuous at negative real numbers, and now we could prove that the function is continuous at any positive real number. That is, modulus function is continuous because it is continuous at every real number. So we can conclude that f is continuous here. So modulus function is continuous. Now let us consider the function f defined by f of x is equal to x square. And here again we can show that f is a continuous function. F is continuous function. Then how to prove it? So again, let C be any real number. Let C be any real number. Then you know function f is clearly defined at x equal to c. That is, f of c is equal to c square. F of c is equal to c square. Then what about the limit of fx as x tends to c? That is equal to limit x square as x tends to c. We cannot substitute x equal to c here and to get a c square. That is not allowed. You understand that in order to find the limit, we can find the value of the function only if the function is continuous. But here we are going to prove that x code is continuous. So after proving that x code is continuous, you can find the value of the function for a limit value. But here we are going to prove it only, so we cannot substitute x equal to c here, and you cannot conclude it is c squared directly. So what we have to do is we have to separate this x code into two identity functions. That is like this. X tends to c. So this will be c only, and then here again c. That is c into c, that is equal to c square. So what we could prove, this is the limit value, and previously we got the functional value, and now it is the limit value. So both are equal. So you can conclude that limit of fx as x tends to c is equal to c square, that is equal to f of c for all c element of R. Here we are not taking any particular real number. It can be any real number. So simply speaking, the given function f defined by fx is equal to x squared is continuous. Why it is continuous? Because it is continuous at every real number. It is continuous at every point in its domain. So we can simply say function is continuous. Similarly, we can prove that every polynomial function is continuous. Every polynomial function is continuous. You are doing the limit computation in 11th class like this. For example, limit of 3x square plus 5x minus 7 as x tends to 2. Can you recollect the method you adopted in 11th class? It was nothing but you are substituting, that is 3 into 2 squared, 5 into 2 minus 7, and you are computing, that is equal to 15. So actually, how can you justify this operation? Because here the demand is a limit. Here the demand is a limit. But you computed this as the functional value too. So indirectly you were applying the property of continuity there in 11th class. That is, instead of finding the limit of a function, you were computing value of the function. That is, the function is continuous. So you were applying the property that the polynomial function is continuous in 11th class itself. That is why it is true. So hereafter you can compute the limit of a polynomial function as the value of the polynomial. Now let us consider the function f defined by f of x is equal to sin x for all x element of real numbers. That is the sin function. We are going to prove that sin function is continuous. We are going to prove that sin function is continuous. Prior to that, we want some basic results, that is limit of sin x as x tends to 0 is 0, and the limit of cos x as x tends to 0 equals 1. So we shall have certain visualization for that and shall come back.
Now let us consider the x radian, and you see mb is the sin x and ym is the cos x. When x becomes 0, what is happening to the height mp? That is sin x becomes 0. And what is happening to ym distance? That is cos x, that becomes 1. So it is very clear that when x tends to 0, sin x, the height becomes 0, and the distance ym, cos x, becomes 1.
Now let us prove that the function f given by f of x is equal to sin x. X belongs to the set of reals, that is the sin function that is continuous. We shall prove this function is continuous. Clearly, sin x is defined for any real number c, and f of c is equal to sin c. Thus we have the value of the function. Now what about the limit of sin x as x tends to c? So here we cannot put it directly, that is say sin c. Why? Because we don't know whether the function sin x is continuous. Then only we can have the value of the function in place of the limit value. So here we have to apply some other technique. So here x tends to c. X tends to c means x is approximately c. So why don't we put the actual value of x, that is c plus h. So here it is very clear that as x tends to c, then h becomes 0. So using this concept, we can write limit of sin x. Sin x, what is x? X is c plus h. So we can write a c plus h, and h tends to 0. That is limit of sin c plus h as h tends to 0, that is equal to, that we can expand. We know the expansion of sin a plus b. So using that, we can have limit h tends to 0, that is sin c cos h plus cos c sin h. So we can have the value here, so that is equal to, we can take a sin c outside, that is limit h tends to 0 cos h plus, here we can take a cos c outside, then limit h tends to 0, then we have sin h. And we already seen that limit of cos h as h tends to 0, that is 1 only, and this limit of sin h as h tends to 0 is 0. So using this concept, we can simplify this thing to get a sin c. So what we could prove is that limit of fx as x tends to c, that is equal to sin c, and that is equal to f of c. So that is the limit value and the functional value of the function are same at x equal to c. Therefore,